Alright, welcome. This is more of our unit on forces. What I'm going to do now is demonstrate a few free body diagrams for you to sort of give you an idea how they work. This is an old worksheet that we had from last year, I think. And so if you follow along and try to do these yourself before I explain them to you, you should be able to pick this up fairly quickly. It's not difficult. So this uses a document called the method, which is basically what we call the method for drawing free body diagrams for objects in these dynamics problems. So these mechanics problems. Sorry. So I would encourage you to read that if you haven't already. Otherwise, this isn't going to make a terrible amount of sense. So anyway, let's look at this first problem here. So for this situation, we've got we want to draw the free body diagram and write Newton's second law equation. So we've got this object with a mass of m sitting on a flat surface, and it's accelerating to the right. So, or sorry, it's not accelerating to the right. Acceleration 0 with no friction. So let's draw the free body diagram. Let's see, is this in the right place? Yeah, more or less. Let me move it down a little. There we go. So let's draw the free body diagram for this. So I'm gonna copy the sketch briefly. Got an object with mass m. It's accelerating not at all. Maybe there's a force on it, we don't know, but it's not accelerating. And there's that, and there's no other force on it. So first we can draw in a gravity vector, okay? And we can define our x and y. This is not the free body diagram yet. This is just doodling on the problem diagram. And then we want to, what are the forces on this thing? Well, there's going to be weight, obviously. So we can put that down and say weight equals mass times gravity if you want. And then we're going to have a normal force acting against the weight, right? So otherwise the thing would fall through the ground. So I'm going to call that, actually I'm going to call that N, the normal force vector. And weight is mass times G. And other than that, I think we're all in pretty good shape. So so let's go ahead and draw our free body diagram. So over here, I'm going to write FBD for the box. Oops, and I'm going to spell box correctly this time. There we go. FBD for the box. So the first thing you do is you draw a point to represent the box, and you copy your coordinate axes over. So y, x, and now what we want to do is we want to look at what the forces are, and we draw them all as arrows, sort of pulling on our box. So there's our weight equals mg, and our normal force. Okay, well, normally the second step would be to break this down into components and do a second free body diagram, but the weight acts straight down along our negative y-axis. Normal force acts in opposition to that straight up. So, we don't really need to, because everything is broken down into components. They all just have y components. So now we want to do our, let's see, what did we want? We wanted write Newton's second law equations. So let's excuse me. Let's go ahead and do those. So we know that the sum of the forces on the body equals mass times acceleration. I'm going to do the vector version first, but this is so easy. So we can say the normal force plus the weight equals mass times acceleration. Okay. But that our acceleration is 0 actually, so probably could have written 0 in before, but what the hell? Normal force plus weight is mass times gravity, so mass times our gravity vector equals mass times 0, so really just 0. So what that's going to tell us is that the normal force equals the negative of mass times gravity, which is also equal to the negative weight. So normal force is going to be equal to weight acting in the opposite direction. And there we go. Basically, we're done. I guess maybe one more step would be to equals let's see, negative mass, and then gravity here. The gravity vector is going to be negative gravity scalar times j hat, because it's the gravity scalar is the magnitude of our gravity vector, and it's acting in the negative j hat direction. So normal force is negative mg j hat. So we didn't really give, there's no problem statement there. There's no problem we're supposed to solve, but there you go. If we wanted to do this in scalar form, we would do sum of forces in the y direction equals m times acceleration in the y direction, which equals 0. And so then the normal force acts in the positive y direction, so normal force minus the weight equals 0. So really, or minus the magnitude of the weight, equals 0. So really, you could say the magnitude of the normal force is the magnitude of the weight. So there you go. Pretty easy, obviously. So let's move on and do a somewhat harder one. And somehow I need to minimize that. There we go. So let's scroll down and find something that has. Ooh, here we go. So let's do something where we have, say, let's do this one. Hardest one there. All right, so we got this force acting at an angle theta. There is friction. We got mass and we got constant acceleration. So let's get this back and scroll this down a bit. And we've got our angle theta. There's our force. There's our block with a mass m. And we do have friction. And is this thing accelerating? I think it is. Yep, A is constant. Great. Okay, so A equals constant. All right, fantastic. So let's put in. Let's draw it down here. Let's draw our y and x directions. So we have our coordinate axes, and now let's do a free body diagram on this puppy. So FBD for the block. Label it. Okay, right. However you want to label it. We'll draw our coordinate axes in again, y and x. We always show those so that we know, what our directions are. Here is the dot indicating, dot representing the block. The weight is acting downward, so we do that. We can say, I'm just going to call it mg. Weight equals mg. I'll tell you what, w equals mg. Why not? Okay. We have a normal force acting upward, so I'm going to make that n, going straight up. It's perpendicular to the surface of the ground. We've got acceleration is constant, but that's not part of our thing, right? So sketching them over here, there's weight, there's the normal force, and then there's a force due to friction that's going to act this way. If it's accelerating to the right, that means it's moving to the right, and then the friction is going to act in that direction, act to the left. So actually, we don't know for sure that it's moving to the right. It could be moving to the left and like trying to slow down. So the acceleration would be slowing it down as it's moving left. But in that case, the friction would be pushing against the direction of its velocity, not the direction, of its acceleration. But we're going to assume that it is going to the right. So force of friction is going to act this way, right? So there's your F sub F. And then the force, this F force, just F, is going to be acting in this direction at an angle theta. Okay, so that really is our entire first free body diagram. Sorry, pardon me. Our entire first free body diagram. Now we want to break this down into one that has everything done in component directions. So we do a second free body diagram. If we put it right next to the first one, we can, conserve the coordinate axes and use the same coordinate axes, so we don't have to redraw those. And so we're going to put in everything that goes along a coordinate axis, we just copy over. So mg there, and force due to friction. And then here, our F force gets broken down. This horizontal thing is going to be F times cosine of theta. So that's the component of this F that goes horizontally. And then vertically, we're going to have F S sine, great, F sine theta. So there we go. And you can make it a little bigger if you want. If you want more room for arrows to come out of it, you can make your dot bigger. You know, it doesn't need to be pretty. It just needs to be clear. It needs to show all the forces and their components that are acting. So now we've got them all resolved into x and y components. So it's easy to write our Newton's second law equations. If we want to write one in vector form, and you don't have to, but you know, I'm going to do it just to show you. So this is going to be basically just going to be, you know, a bunch of vector addition: n plus force due to friction plus weight plus this F force equals ma. All right. However, you know, now that we've done this horizontal and vertical thing, it's easier to just write the scalar stuff. So let's do sum of forces in the x direction. Okay, so in the positive direction we have F cosine theta. In the negative direction we have force due to friction. And what does that equal? That equals, great, there we go. That equals mass times our acceleration in the x direction. All of our acceleration is the x direction. From the diagram here we were shown constant acceleration to the right. So we can just say ma in the x direction. All right, so this is F equals ma in, you know, this is just sum of F equals ma applied to here the x and then here the y. Okay, and then sum of forces in the y direction equals, so let's see, we have n going up, normal force, okay, plus sorry, no, not plus, that's the only one going up, so the rest will be minus, so erase that, there we go. All right, normal force minus mg, which is a weight, minus F sine theta equals 0. And there we go. That's it, basically. Those are our you know, two scalar equations. Let's see. There we go. There's our two scalar equations, and that's all we need to do. And then, you know, once we learn a little bit more about friction, this will not be hard to solve. But for now, you know, it is what it is. So there you go. I'll probably try to solve another problem or two that are a little bit harder, just to give you a couple more models to work with.